we're in the same boat. Although I don't think there's a mandate yet for faculty and staff to get vaccinated. Although any faculty and staff that doesn't get vaccinated, I don't know what to say. It's not very logical. Are there any questions?
Oh, yes, I have a few questions. I want to know more about the exam concerning whether it's open note, its specific date, and maybe how we could prepare the best.
Okay, so I don't know if everyone heard that. The question was about the exam. If we go at a reasonable pace today, we will finish the material for the first exam today. Otherwise, it might overlap into the next class, which is on Wednesday. And I imagine the exam would probably be roughly a week later, maybe, so either a week from Wednesday or the following Monday. We'll see how, basically, I don't want to fix the date until I see that you get your homeworks back. I want to make sure that you have your homeworks back before we have the exam. So, but those are the most likely dates, a week from Wednesday or 2 weeks from today. My exams generally are open book, but only our textbook and only a hard copy. No computers, no calculators, no phones. No one's allowed to have a phone that they're using during the exam. If you take out a phone, you have to put it on my desk. Don't worry about the numbers. Anything you can calculate on a piece of paper on this exam. Generally, there are 3, sometimes 4 questions, they're problems to work out. They're open notes, but only the notes from this class. No homework solutions, no downloaded problem solutions from the internet. And what I do is I go around and I look at your notes. I check. So make sure you don't have anything else but the class notes, nothing else. Make sure of that. Because when I go and I look at everyone's notes, and then I find a compendium of every problem ever solved in history from the internet, and they say, oh, I didn't know it was there. That's not credible, okay? So it's open book, open notes. The best way to prepare for an exam is to do problems. Obviously, you have to go through the class notes before you do problems. As you'll notice, mostly I'm following the book, but I add lots of things, both explanations and derivations. Sometimes the book writes things that are supposedly obvious, and then I go through and I show where they came from, which they don't necessarily do in the textbook. Sometimes it's stuff that you need to know, and sometimes it's stuff that you just should know for your own education. For example, when I derive the more general CSTR equation for the non-constant density system, I'm not going to test you on that, but it's nice to know where they came from because a lot of systems are non-constant density. And the special case is the constant density. Does that answer your question, or do I
have a follow-up. I have a follow-up.
Go for it.
We often take our notes on these iPads. Can we print out our handwritten
You can print them
stuff?
out. You can print them out, but no electronic devices, because that's a good way to communicate between students. It's a good way to communicate with the internet and to other people. No electronic devices. You can print out whatever you can print it out on paper. The notes from the class and the textbook, a hard copy of the textbook. Are there any questions on that? I hate to be so 1990s with hard copies, but again, it's just too tempting to query other people or the internet on an electronic device during an exam. Okay, are there any? Yeah?
Is it possible to request that the test is on Monday instead of that Wednesday? We have a test on Tuesday and Thursday next week, so if it's possible to have a test on Monday instead of that.
That's the more likely date in any case. That's the more likely date. Again, I'm not married to any one particular date. There's always a little bit of wiggle room depending on your schedule.
I think Columbus Day is that Monday, and we have off, so it would have to be that Wednesday.
All right, we'll deal with it.
Okay.
Are there other questions? I don't want to make the exam too far removed from the end of the material from the first exam because, I was a student too once. basically when there's an exam on material that ends on a certain day, until that exam's over, people ignore all the material after that. You know, it's a natural reflux. It's not a foible on your part, it's just a natural tendency. And I don't want to be halfway through the material for the next exam before this current exam, because people will never catch up then. So there is a balance there. Another question. Okay, I'm warm. Get rid of this sweater. Other questions? Okay, again, interrupt me whenever you like on questions. The more questions, the better. It shows me that you're interested. When you ask questions, it shows me that you're interested in the material. And there's no better motivation to learn something than being interested in it. It's the best motivation. Okay, if you remember, we weren't really doing a lot of control yet, we're doing modeling. And we started modeling chemical engineering systems, mathematically modeling them, and doing the analysis on that. And the reason we're doing that is because first we need a model in order to put control into the model. So we need to know how to do modeling and how to analyze the model. And you might have initially said the first day of class, isn't that what we've been doing since we started chemical engineering, since 228? Yes, except from 228 up until this course, all models were in the imaginary world of steady-state land. And we're not in steady-state land anymore. We're in the real world, unsteady-state land. So, in unsteady-state land, there are DDTs that you don't just throw away. You have to deal with them. And therefore, the equations get more complicated. So therefore, we're looking at methods of we're going through methods of analyzing unsteady equations. That's what distinguishes this class from previous classes. If you like mathematics, that means finally enough of those boring steady-state equations. Now we get some really good unsteady equations. If I haven't quite converted you to that way of thinking, I'm working on it. Okay, so in unsteady equations, we found that many of our equations were linear first-order differential equations that we saw so far. And for linear first-order differential equations, they always took this form, and we solved them once and for all. Where we have a of t and b of t, if they happen to be constants, then we just get exponentials as solutions. If they happen to be explicit functions of time, then we get this solution where we have to actually do the integrals for any particular choice of a and b. Now, unfortunately, even in unsteady state land, the real world is not just unsteady state land, but it's often nonlinear land. So even though here these equations were linear, meaning you never see more than one y in the same term, real life is not only unsteady state land, it's nonlinear land. By the way, I'm getting this terminology. I don't know if you ever read the book Flatlands. Did anyone ever see? It's a nice little paperback called Flatland. I don't know, it's decades old. But it's written for the layman to give the layman the sense of what it would be like to live in a two-dimensional world. And it's really a neat book. You could read it in one day on the weekend. It's not really equations, but it gives you a way of imagining you lived in a two-dimensional world or a one-dimensional world, and what life would be like. So that's called Flatland. So I'm using some of the analogy, nonlinear land, etc. I recommend that book. It's a Dover paperback. It doesn't cost much. Oh, okay. There's probably a PDF of it. Okay. So when equations are nonlinear, that means that you have curves that look like the white curve here. And this method no longer works. Now, sometimes we're lucky and you can solve a nonlinear equation, but there isn't this general way that you can solve it once and for all. And many times we're not lucky and you can't solve it analytically. So you have two choices. If you can't solve it analytically, you can either solve it numerically, and we'll discuss that in a little, either the end of this hour or the beginning of the next hour. Or you can try to linearize. What is linearizing? That says, if you have a curve that looks like this, like the white curve, sometimes you can approximate the white curve. If you're pretty close to CAN, you can approximate the white curve by the blue curve, which is the tangent. And the tangent is a straight line, so it's linear. So the idea is, as long as I don't get too far away from CAN, the blue curve is a pretty good approximation to the white curve. Obviously, if I'm way out here or way over here, it's a terrible approximation. So that's sort of pictorially what's going on. Where does that picture come from? That picture comes from Taylor's theorem, good old Taylor. And Taylor, without going through the fussiness that I did last time, basically says, if I have a function that's sufficiently differentiable near a certain point, then the function at any point in the circle, you don't have to write, we've done this already, is equal to the value at the center plus a correction. The first correction is the derivative at the center, which I'm assuming exists, times z minus z0. This is a linear term in z. And if I want to do even better, I can go to a second derivative, evaluated at the center, times a quadratic correction, plus etc. And I can make this an exact equal sign because I have an exact expression for the error if I truncate the series. I don't need an infinite number of terms. I can truncate it. Now, of course, this involves the value of the n plus first derivative somewhere in the circle, and somewhere, it's guaranteed that there is a point z star somewhere in the circle, it just doesn't tell you where. So, but it gives you a way of giving a bound on the error. It tells you what the maximum value of the error could be. So as long as the maximum value isn't too big, I'm okay truncating. So we use this theorem, and we truncate after the first term. So that way, we approximate this nonlinear function by a constant plus a linear function. Once we approximate it by a linear function, we're back in linear land. We're still in unsteady land, but unsteady linear land. So that's the basic idea. And we wrote this out both for many dimensions. Here it looks like it's one dimension, here it's two dimensions. First, we started doing a problem, which there's only one independent variable, so I only need a term that looks like this. After we finish this problem, we're going to go do one where there are two independent variables. Are we all clear on the same page? Sorry I'm making your life difficult by moving back and forth here. But that's life. Any questions? Okay, so what's the idea? We have a CSDR. It's great that no one else uses the blackboard in this room. Everything stays on the blackboard forever. There was a room, just an aside, there was a room in Baskerville that probably about 7 or 8 years ago I taught a class in that room, and then they took the room offline, so it wasn't being used anymore. And I went in there like 5 years later, and my bad handwriting was still on the blackboard. Then, of course, they destroyed the room and took out all the blackboards. Different story. Okay, so here's the CSDR, and here the assumption is that I have a second order reaction where the rate function is kCa squared, 2kCa squared. And we wrote out the CSDR equation, and we assume we're looking at the response where I have a system that's at steady state at one value of CAN for t less than 0, and then we do a step change to another value of CAN, a higher value of CAN. And we want to know the response of the system. Notice I'm using this cumbersome notation rather than what you have in the book because this is more explicit. You don't have to guess what CA0 is. So this is CAN for t greater than 0. This is CAN for t less than 0. It's a little more writing, but there's no guesswork. You know exactly what it is. And so what we do is we notice this equation is nonlinear, so we had to write CA squared. We had to linearize it. Well, we did that over here. And here we write this nonlinear term CA squared as a constant plus another constant times CA minus CA0, and we drop the remainder term. So that's linear. We plug that in, and we rearrange. We plug that into this equation, we rearrange, and we got dCA prime dt plus this thing. The 1 over tau is what we got from the flow term, and this is what we got from the linearization. So the linearization was the 2CA0. Here, CA0 is CA for t less than 0. I had a 2CA for t less than 0 times another 2K, which gave me the 4K. CA prime plus CA in prime over tau, where I define the prime as deviation variables. So they're deviants. They're how much they've changed from the value before t is equal to 0. And we noted that this is exactly the same form that our favorite form here. And in particular, it's the really favorite form because this is a constant. CAN prime was this value minus this value, so it's just a number. And tau is a number, k is a number, CA for t less than 0 is a number. So it's exactly the form where a and b are constants. And this is where we ended last time, but we noted that this particular quantity here, which is a, which is not a function of time in this case, does in fact depend on t, the value that CA had for t less than 0. And we noted that this was the inverse of the time constant. So 1 over the time constant is exactly this. So the time constant, which remember the time constant in a first order system only depended on the system, not on any of the inputs. It was a characteristic of the system, not any of the inputs. That is a property of linear systems only. What you see here, so if I have no reaction, tau does not depend on the inputs. It just depends on the volume and the volumetric flow rate, which are not changing. If I had a first order reaction, if you remember, the time constant was 1 plus k tau over tau. Tau we said is a constant, and k is a constant. It's the rate constant of the system. So in a first order reaction, which is a really inherently linear system, again, the time constant does not depend on the things that are changing in the system, which is CAN. Notice here that the time constant is tau divided by 1 plus k tau. It's smaller than tau. Well, we said, clearly the time, by virtue of having a reaction, the way A is going to change is not just due to flow, but also due to reaction. So the reaction speeds up how quickly, the time constant, how quickly things change. In the inherently nonlinear system, even once we've linearized it, the time constant now depends on CA for t less than 0. The fact that I have it's a constant, but it's a constant of the thing that eventually will change. That means it wasn't naturally linear. But again, I can rewrite this as 1 over, I can multiply top and bottom here by tau. And if I do that, I have 1 plus 4k CA t less than 0 tau. So again, t is tau divided by this. It's again tau divided by 1 plus something. So it's smaller than tau. So again, it's faster than just flow due to reaction. But again, the amount that's faster depends on this CA and t less than 0. Are there any questions before we get to new material? Okay. So,
I have a question. Can you just remind me what exactly is the time constant in this case?
what exactly is the time constant?
In this case, for the second order.
T. T is tau divided by this. This is an expression for 1 over t. Capital T I'm reserving for time constant.
Okay, got it.
And you can see the time constant is smaller than tau. It's faster than tau, because I also have reaction.
Yeah, I'm just a bit confused on how.
You're confused about?
The CA primes and the CAN primes, where do they come from? Because
The primes mean the actual value for t greater than 0 minus the value from t less than 0. It's the amount things have changed from before t is equal to 0. So this is the definition. Whenever you see a colon before an equal sign, that's the mathematical way of saying definition. Other questions? Okay, so let's plug in. If I plug in to this equation, I have CA prime of t is equal to, it's equal to CA prime, and now you see why I like CA prime. CA prime, in this case, the action's happening at 0. So when I plug into the formula, T1 is going to be 0. When I plug into this formula, T1 is going to be 0. Y is going to be CA prime. Okay, so I have CA prime of 0 times e to the minus a times 0, e to the minus at. E to the minus this thing times t. Plus b over a. So b is CA in prime over tau, divided by a. A, we said, is 1 over t, so it's just this. 1 plus 4k CA t less than 0, tau divided by tau. Cancel those. Times 1 minus e to the minus t over. I just got that by appealing. I didn't have to solve it. I just went directly here because they were constants. Now you'll see, what's your name? Omar? Omar, now you see why I like the primes. Why do I like the primes? Because CA prime of 0 is CA of 0 minus CA of 0 is 0. By definition, this is 0. That's why I like the primes. Because instead of having 2 terms, I only have 1 term. Much better. I like fewer terms means fewer chances of making a mistake. The more you write, the more likely you make a mistake. Okay, so I have this thing, CA prime of t is CA in prime divided by 1 plus 4k CA of t less than 0 times tau, times 1 minus e to the minus little t over big T. So what does that look like? So remember, let's copy this over. CA in versus D, 0. And now let's look at the corresponding CA versus D. So I had some value, 0. I had some value. And now what's going to happen? Now I have this solution, which is 1 minus an exponential times a constant. It looks like this. And this is the linear solution, the linearized solution. If I would actually use the nonlinear solution, I claim it would look like this. So if I kept the CA squared, I claim it would look like that. How do I know that? Well, the first thing I know is as long as CA doesn't get very far from CA in, there isn't going to be much of a difference. So, at first, once I introduce the step change, nothing's changed yet. So CA hasn't gotten very far from CA in. So initially, in early times, these curves are going to track each other. But eventually, CA is going to get far away from where it was before. CA prime is going to get far away from, CA of t is going to get far away from where it was before. The further away it gets, the more these are going to converge. The further away I get, the worse it's going to be. Now, let's remember, how am I approximating the rate function? I'm approximating the rate function, where is it? Over here. I'm approximating the rate function as 4k CA t less than 0 times CA minus CA t less than 0. The real rate is minus 2k CA squared. Here, effectively, I have a CA surviving, but instead of the actual CA squared, I have the actual CA times CA of t less than 0. CA of t less than 0 is lower than CA because CA in was lower before t is equal to 0 than after t is equal to 0. So by replacing one of the CAs by the old CA in, I'm underestimating the value of CA squared. Let me just finish the sentence and then. So if I'm underestimating the value of CA squared, that means my rate of depletion of A is going to be less in the linearized system than in the nonlinear system. we'll live with it. But that's why here, the rate of consumption of CA is faster in the nonlinear system than in the linearized system. Because the linearized system is effectively not exactly, but effectively calling CA squared CA times the old value of CA in. But the new value of CA in is a lot higher, so the rate should be faster. Question?
Yeah, I just, for clarification, so CA in prime is a number and not a function.
Correct. Because it's a step function. If this were not a step function, if I had a continuous curve, it would be a function. As you'll see later on in the semester, we'll make CA in go from a constant to a sine function, and then it will be a function. But here, it's a step function, so it's just a number. Yeah.
Well, the value of CA will eventually decrease, right, once you start reacting?
Yes, but the value of CA in the reactor eventually decreases if you think of a steady state system. But what we've done is we've raised CA in to a higher value. So the new steady state is going to be higher than the old steady state because I have a higher CA in. So you're thinking in steady state land. We're in unsteady state land.
I guess I'm confused why the concentration of A is increasing if it should be reacting away.
Because we're not looking at we're not taking a batch system where we're looking to concentrate with an initial charge and looking at how CA changes with time. If I take a batch system, fill it with a bunch of A, and the amount of A is going to decrease with time. What we have here is a flow system where I have a CA coming in, and a certain amount of CA is coming out, but that the amount coming out is less than the amount coming in. So if I look at out, in, and out is lower than in. But now what I'm doing is I'm bumping up in, so I also bump up out. Out is still lower than in, but it's higher than it was before. So what I'm doing here is I'm not comparing CA, this curve does not compare CA out with CA in. It compares old CA in out with new CA out. So maybe I should make that explicit. New CA out with, old CA out with new CA out. Now remember, CA equals CA out because it's a CSCR. But this value is less than this value, and these values are less than this. So to make that explicit, CA for t less than 0 is still less than CA in for t less than 0. And CA for all time greater than 0, including at infinity, is still less than CA in for t greater than 0. So this says exactly what you were saying.
So you were just telling us how the solution you get by linearizing will overestimate a little bit. Is that going to be true anytime?
No, we'll underestimate the rate of reaction and therefore overestimate the amount of CA.
Okay.
It underestimates the rate of the rate I'm chewing up A, so therefore it overestimates how much A I have left.
Okay, and will that be true in general?
No, every system is different. That's in this particular system. Other questions? Okay, so is this clear? All right, so time for me to start erasing things. And starting anew. So I'm going to erase this. This is from last time. Okay, so why don't we do another case that is similar to this in the sense that there's only one thing that's varying. Only one independent variable. Here we're seeing in prime. Let's look at a tank, another tank, where I've got fluid flowing in and fluid flowing out. And I just want to look at the height, h as a function of time, and this is, say, the cross-sectional area. Okay. So if I do a balance So I've got fluid coming in and fluid coming out. So this is V in, and this is V out. I think in the book they call this L, so there's no reason for me not to use their notation. Okay, so if I want to look at the volume, how the volume changes with time. What's the general equation of chemical engineering? All of chemical engineering summarized in one equation? What one person, right?
Accumulation, time in, time out, generation.
Yep. So accumulation here is dV/dt. I need in minus out and net generation. But there's no generation. I'm not creating fluids. There's no reaction. So given constant density, no reaction. So all I have is in minus out. In is V in, out is V out. I was using subscripts. Okay, now let's notice that V is the cross-sectional area times dL dt, and that's equal to V in. V in is given. So here I'm going to assume that V in undergoes a step change minus V out. Now V out I don't know. So notice my unknowns now are L and V out. And I guess a week ago, we discussed various choices for V out. I could have a pump that pumps it out at a fixed rate. Or if I appeal to Bernoulli, I just make a little hole in the reactor and watch it come out. Then I can find that V out subscript could just be proportional to K times the square root of L, where L is this height. And we saw that came from Bernoulli. Now we did that about a week ago. Now I have two unknowns, two equations. So no degrees of freedom left. The amount of equations equals the number of unknowns. Now, unfortunately or fortunately, this is not linear. It's the square root of L. But luckily, we've linearized the square root already. It wasn't just an accident that I chose this example. We saw that the square root of x, the square root of x0, was 1 over 2x0, 1 over 1 prime, x minus x0 plus the remainder. So that's exactly what I have here. I have, this is equal to k times the square root of L for t less than 0, plus 1 over 2 times that, 1 over 2 times that. Times L minus L of t minus L of t less than 0. Plus a remainder, which I'm going to drop. So because I drop it, it's going to be approximately equal to instead of equal to. So that tells me I can now look at the system for t less than 0, for t greater than 0, and for t less than 0. So again, I'm going to be given that for steady state for t less than 0, just like what I was doing before. So this, we're given that this was at steady state. This is not steady state. Okay, so for t less than 0, let's write this out. So for t greater than 0. So I have dL dt is equal to, well, or a dL dt is equal to V in minus, and this is again for t greater than 0, minus K times root L t less than 0. I'm running out of space here. Plus 1 over 2 root L t less than 0 times L minus L of t less than 0. So I just copied this over and I left out R. So I plug this quantity in for V out. So like, yes?
Could you write a little bit bigger, please?
Yeah, I was trying to here and I was running up at the edge of the blackboard. But I will definitely try. So for t less than 0, so this is the linearized. Let's write out the full of that one for t less than 0. For t less than 0, I've got a dl dt is equal to v in for t less than 0 minus, well, v out is just k squared of L. So for t less than 0, I just have k times the square root of L t less than 0. I don't need to linearize v for t less than 0 because I can just write it this up. If I want to linearize it, I would just get L of t less than 0 minus L of t less than 0. So this term would be exactly 0. So whether it's linearized or not, I get the same thing. Now let's subtract. And this is a method of doing it. You write out the full equations. You linearize it about the previous state. Then you take the previous state, the steady state, and you subtract. So let's notice this is L of t less than 0. So now we subtract, and what do we get? We get a dl prime dt. Remember, L prime is L minus L at t less than 0, and since it was steady state, this is 0, so it's no problem. And that's equal to Vn for t greater than 0 minus Vn for t less than 0. That's prime, Vn prime. Whenever I see greater than 0 minus less than 0, that's the definition of a prime. Not Amazon Prime, Prime Video. Okay, minus. Now minus, notice that this term and this term are exactly the same, so they cancel. So and that's not an accident. Because remember, when I linearize, the first term I get is the value of the function at the point about which I'm linearizing. So the fact that this cancels is not at all a coincidence, because I'm saying L of t, or the function of t, is the function it was before, which is what I have here, plus this linear change. So these cancel, and what I'm left with is k over 2 square root of L at t less than 0 times L minus L of t minus t less than 0, which is exactly L prime. Question? Yeah.
What is K?
K, we said, is just that constant, which from Bernoulli's equation, we had a value for that. But empirically, so remember, from Bernoulli, if you look back at the notes, you'll see from Bernoulli's equation, we had a value for that. It turns out empirically, Bernoulli's equation doesn't hold exactly, so when you actually do a problem, you measure that constant. It involves G. It's like 2G or something, I forget exactly. So you typically measure K rather than just relying on the constant from Bernoulli's equation. Well, notice this now just becomes dl prime dt plus k over 2a square root of L of t less than 0 times L prime is equal to v in prime divided by a. And this is exactly of the same form I had here. Here I have b is this thing, this is a constant, and a is a constant. And notice my time constant now is just 2a square root of L of t less than 0 divided by k. That's my time constant. Because remember, a, the square bracket is a, that's the inverse of the time constant. And again, this time constant depends on the value, the initial value of the variable that changes, which is, again, a definite sign that it used to be nonlinear, that it's a linear approximation of a nonlinear problem. And what you can notice is that the higher it started out, the faster the time constant. Because the higher it started out, the faster the liquid flows out. Any questions on that? Yes?
So it's, when you say greater than zero, minus less than zero, that's just equal to zero? Or is it-
Yeah, less than 0 and equal to 0. What I really mean is less. I haven't defined really what happens if t is equal to 0. If t is equal to 0, you jump from here to here. So what exactly is the value at 0? You could say it's this one or this one. But so that's why I used less than 0. It's before the step change. Because at that particular point, t is equal to 0, what is it? It's actually changed already. But I want to refer to the value it was before it changed.
Why do we drop the R?
Because the r, the remainder term, which comes from here, the remainder term is something that we would need. We don't know the remainder term exactly because we don't know the point c star. The usefulness of the remainder term is even after the fact, even after we do the problem, to see how good the approximation was. Since we don't know z star, what we can say is, what is the maximum value in this circle of the n plus first derivative, in this case the second derivative? And then we can say the error is less than the maximum value of the second derivative in this circle times 1 over n factorial times z minus z naught to a power. So the usefulness of the remainder is not in doing the calculation, but in estimating the error. And that we can do in a separate calculation. In this course, unlike a course in numerical analysis, we don't often estimate the error because we should, but we're delinquent, not deviant. Delinquent. Other questions? All right, so let's plot this. So this is Blackboard 1. Let's look at Blackboard 2. Now we need to plot. T, 0, 0. Here is V in. Here is L. V in goes up, and what happens to L? Well, obviously, if I increase the input, I'm going to increase the output. So again, I didn't even write out the solution. So let's write out the solution. The solution, L prime of t, is equal to L prime of t is L prime of 0. Again, by using the primes, y of t1 is always 0. So again, in this case, t1 is 0, and L prime of 0 is 0. So L prime of t is equal to b over a, so that's v in prime divided by a, divided by k divided by 2a square root of L of t less than 0. And here the a's cancel. Times 1 minus e to the minus t over big T, where big T here is you see big T. So again, the solution looks like this. Obviously, I increase B in, I increase L. And notice, even though I solve for L prime, L is equal to L of t is equal to L of t less than 0 plus L prime of t. So when I have L prime, it's no problem. I just add this constant to get L. And let's see, which one's higher in this case, the linear or the nonlinear? The Linear is lower. I think in the book, V went down. Okay, well, if V goes down, then L also, it's the same curve. All what happens is I change the sign. If V prime is negative instead of, so here V prime is positive, V in prime is positive, here V in prime is negative. So in this case, if V in prime goes down, L goes down. That is, I'm just changing the sign of V in prime. So I go to a new steady state. And let's just note that if I have the nonlinear one, it would look like this, nonlinear, linear. And why is that? Well, if you remember, the actual value goes as the square root of L. So when I approximate the square root of L by the square root of L, by L minus L prime, the square root of L goes down slower than L does. The square root of L goes down slower, so, or it goes down, when I'm using this case, I'm approximating the square root of L by its initial value plus another part. But the initial value has a higher L than the L along the way. So I'm overestimating the square root of L when I approximate it by the square root of L for t less than 0 plus something else. So since I'm overestimating the square root of L, the linear one gives me a lower value than the nonlinear one. Are there any questions on this? This one is very similar to the last case we did. It's just we're dealing with L's instead of concentrations, but it was the same idea, only one variable. Questions? Okay, so now we're ready for a more complicated one. When I say more complicated, there was only one thing that was changing here. One forcing function. That is, I force by changing the in, and I look at the result by changing L. Forcing the in, one forcing function, and one result, one dependent variable. Now let's look at a case where there are two functions that could be forcing. In which case I'll leave this rather than this. Any questions yet before we go on to that? So, example, a CSDR heater or cooler, whatever, heater cooler. And here's the basic picture. So I've got something going in and something going out. And in addition, I have a heating coil. And I have, and what I'm going to, we're given, okay, so now I've got a volumetric flow rate of the coolant, a CP of the coolant. Those are the things I have. Here I'm given a volume of the reactor. I've got a CV or CP of the flow, and this is a hat. So hat is per unit volume. And I've got a volumetric flow rate of the fluid. Notice the volumetric flow rate of the fluid, a volumetric flow rate of the coolant. And we'll see, and obviously a density. I've got a density. And here I have a density of the coolant. The coolant fluid need not be the same, is in general different from the actual fluid. So, and what we'd like to see is we're given that the volumetric flow rate of the coolant changes at t is equal to 0. And what we want to find is what happens to, for example, the temperature at the outlet. The temperature of the fluid as a function of time. So notice here I have a temperature of the fluid, T in, and here I have T, and here I have a TC in, and of course here I have a TC out, where C is the coolant. So is it clear? I've got a whole panoply of variables for the fluid in the tank and the coolant fluid. All the coolant fluid guys, variables and parameters, have a C on them, and all the other ones that don't have a C apply to the fluid in the tank. Are you with me? Okay. Now, we're going to assume that the tank is a lot bigger than the tube here. So we're going to assume that the tank volume is much bigger than the volume of the coil. And we're going to guess, we're going to assume that the coil reaches steady state much, much faster than the tank. So when I make a step change in, for example, the flow rate of the coolant, I'm going to assume that the coolant, that this coil, I can get away with the steady state balance here, whereas for the tank is so much bigger, it takes a lot longer to reach steady state. So I need an unsteady balance for the tank. So what that means is tank is unsteady, while the coil is almost steady. So if you like, I use a pseudo-steady state approximation on the coil, but not on the tank. See, I like to introduce my assumptions right at the beginning. Clear? Are you with me? Now the other thing is, and let's note, that the coil has a certain overall heat transfer coefficient. So I've got a U times an A, where A is the area of the coil. This is for the coil. It turns out that the heat transfer coefficient for the coil depends on the coolant flow rate. It's not just a constant. And that's empirical. I'm not giving you a theory for that, that's from experiment. And typically, this depends on VC. And we can often approximate it as alpha VC to the beta, where alpha and beta are constants. And that's empirical. That's not the result of theory, that's empirical. Okay, so given all that, so let's notice something. We expect things to be nonlinear here, because as long as beta is not 1, clearly this is going to be nonlinear. A is going to be a nonlinear function of VC. Plus, who said UA just appears on its own? UA itself may appear in some nonlinear way. Just setting it up. Are we happy with the setup before we start writing equations? Okay, we're going to do an enthalpy balance, and we're also going to assume that the work I can ignore and the potential energy are negligible. So I have the HDT. Let's do a balance on the tank. Unsteady state tank balance. The HDT is equal to H in minus H out plus Q, where Q is positive when heat goes from the coil to the tank. Where I define this as greater than 0 when heat goes from coil to tank. Again, this is in minus out, plus here I have generation. Well, actually, this is in. I still have an in. There's no generation. There's no reaction. No reaction. So these two are in, and this is out.
Why are we doing an enthalpy balance?
What's that?
Why are we doing an enthalpy balance again?
Because we're interested in the temperature at the outlet and in the reactor. Other questions? So let's write this out. Rho V CV hat dt dt. That's dH dt. That's HA. That's rho CP, actually, rho V CP T in minus T ref minus rho CP V T minus T ref, where I have some sort of reference temperature for my enthalpy, plus Q. And I'm going to assume that CV and CP are the same. I kind of want to leave Taylor's theorem up there, so I'll end up erasing that back. Okay, well, now let's do a steady state balance on, so here I have the balance on the tank. Now let's do a steady state balance on coil. Well, on the coil, it's the same idea, but the left side is 0. And so what I have here is I have, and notice, by the way, the T ref cancels. It's the same in both of those. So when I write the steady state balance, I'm not going to bother with T ref. So here I have a rho coolant, CP coolant, V coolant, times T in minus TC in minus TC out. So this, instead of being T, is now TC, it's the coolant. This, we're no longer in a CSTR, so it's the out. And now it's minus Q, because Q was positive when it went from the coil to the tank, but now we're looking at the coil, so it's negative. Okay, and then here I have UA. So what am I going to do here? So what I'm going to do, first thing is I'm going to divide through by rho V CV. And if I do that, this cancels, the rho CP cancels, the rho CP cancels, and this becomes 1 over tau, and this becomes 1 over tau. And here I still get the rho CP hat times volume. So that was just a little bit of algebra. Now, what do I need to do? Well, what I would like to do, I think I left out one equation. Let's see. I need another equation. Yes, I have another equation. How many equations do I have? How many unknowns? I need one more equation. So I don't know T. I don't know Q. And I don't know TC out. So what's unknown so far? I don't know T. I don't know Q, I don't know TC out. I know TC in. I don't know any of those. And I need to, and obviously, okay, and I don't know UA. So So there are 4 things I don't know. How many equations do I have? I got 1 equation for UA, 1 unsteady balance, and 1 steady balance. So far only 3 equations. So I need a 4th equation that relates Q to UA. So here I yield to unit operations, and Q is UA delta T, but let's do it for the coil. So remember, heat is going out of the coil. So I need a minus sign here. And then it's, normally I would say it's UA delta T coil log mean. Log mean. And that you learned in unit operations. But log mean has logarithms in them. And the logarithms are nonlinear. So I don't really want to do that. See, I'm doing on time. So let's approximate this. Let's see if we can come up with an approximation for delta T log mean. And to do that, I think I'm going to erase the other blackboard. Have you taken a picture of this one yet? This would be UA times the integral over the whole coil. So dx from 0 to L of T minus T in the tank minus T in the coil of X. Now, since T is T in the tank, and the tank is well mixed, it doesn't depend on X, because the tank is well mixed. Well, now just for fun, I'm going to multiply and divide by L. If I multiply and divide by L, so I change variables from X to X over L, then this becomes from 0 to 1. Now, what does this say? When I integrate a function and divide by 1, so I integrate from 0 to 1 and divide by 1, that's like adding up all the test scores in the class and dividing by the number of students. What do I get when I integrate or add up and divide by the number of students? I get the average. So this thing here is the average of T minus TC over the coil. And I'm going to approximate that average by the value at the beginning and the value at the end divided by 2. Really, I should do the exact average by integrating everywhere, but that's nonlinear, and we're not doing nonlinear in this class. So we're going to approximate this by minus UA times the value of T minus TC in plus T minus TC out divided by 2. And I probably should have had the TCs. No, that's correct. So this is our approximation. And this is the final equation that we need. So let's now go over here and make this blackboard 3. Okay, I got 4 equations. I got to combine them. So what's my strategy here? My strategy is going to be, I want to eliminate TC out. So I want to solve this equation for TC out as a function of TC in and Q. And plug into this equation. Okay? So in that way I'm going to get rid of TC out. So let's, again, rewrite that last equation. So I've got Q is equal to minus UA times 2T over 2 is just T, minus TC in plus TC out over 2. So I just rewrote that last equation. where I for no reason write t twice. And let's take this equation and solve for TC out. So again, I've got Q is equal to rho C C P C VC times TC in minus rho C C P C VC TC out. So I can solve for TC out is equal to Q, let's move this to this side of the equation, this to that side of the equation, and divide by rho CPC TC. So it's equal to TC in. So I move this to the left, this to the right, and divide by rho CP V. So when I divide by this, I just get TC in. And now I'm subtracting Q over rho C CPC VC. So this just gives me TC out. And now what I'd like to do is I'd like to plug this into here. Okay, so now I plug star into star star. So that tells me Q is equal to minus UA times T minus TC in plus TC out. Well, TC out is equal to TC in plus something. So the first term, I'll just have a TC. Because I have TC in plus TC in over 2. 2 TC in over 2 is TC in. But then I have minus, this was TC in. Now I still have a minus of this thing. Minus and minus is a plus. Because I'm subtracting TC out, so minus and minus is a plus. So if I haven't made any mistakes, I've got a 2 rho C CPC VC. Are you with me? I plugged these two terms into here. One of them was a TC in, which gave me 2 TC in over T2 is TC in. And the other one was the minus this, which came in with the minus sign, which I just copied here and brought the 2 along. And now let's notice I've got 2 Q's here. So I don't want 2 Q's, I want to solve for Q. So I bring this to the other side of the equation. And let's see how to do that. Let's bring this minus sign in. If I bring the minus sign in, I've got a minus, a plus, and a minus. So I brought the minus sign in. And now I can bring this to the other side of the equation. Factor out the Q, that'll give me 1 plus 1 over this denominator. And divide it out. So that tells me that Q, solve for Q, is equal to. It's equal to UA times TC in minus T divided by 1 plus 1 over 2 rho C CPC VC over 2. Is that clear how I got that? Again, it's algebra here. There was a minus sign here, so I bring it to the other side of the equation. When I bring it to the other side of the equation, I factor out the Q. I get Q times 1 plus 1 over this denominator. And that's what I divide, and this is what was left on the other side of the equation. Now, notice, I can go back to this equation. So I have dt dt is equal to. It's equal to T in minus T over tau. T in minus T over tau plus Q over rho CPV. Plus Q over rho CPV. Well, Q is this. Before go on, I want to make sure this is the form I'm aiming for. Because it doesn't look like the form I'm aiming for.
That's a bit B though, right?
How about, let me think for a second. Yeah, I left out a factor. Sorry, I left out a factor. So let me just fix the factor I left out, and then we'll go back there. And then I'll get to your question. I lost the UA here. So the coefficient has a UA here. So it's 1 plus UA over this. One plus UA over 2 rho C CPC VC. Okay, so that looks correct, and let's just put that in here. So I've got QA times TC in minus T, UA over 1 plus UA 2 rho C CPC VC. You got a question?
No, I was just looking at the B's there. In the blue. There were different B's, but
You have to tell me where you're looking.
in the blue. The Q over.
Blue over here?
No. The Q over C, PC. Over B. Yeah, that's good for B, right?
It's the volume rho times CP, where we said CP and
Yeah,
CP.
but that was regarding before we were writing that backwards. It's about.
I'm sorry, I don't understand the question.
No. I'm saying because you started to write the Q over the rho CPV, and I was just confused as to like how it was going to cancel out. But it's irrelevant because you changed it. That's why. It's
So are you're not confused
no,
now?
I'm good with that.
Okay, so that was Q, and I still need to divide by rho CPV. Or did I do that already? So, okay, so Q we said was equal to this quantity. And now I also divide by, where are we? Rho CPV. Okay, so let's see where we are. And especially we're going to have to see where we are because we're getting close to the end of the hour. Where UA is equal to alpha VC to the beta. So now we've reduced this to 2 equations. We've eliminated TC out, and we've eliminated Q. So notice we went from 4 equations to 2 equations by eliminating Q and TC out. We can always go back and calculate them, but we combine the equations to get rid of two of the four variables. So we only have 2 equations left.
I'm a little confused. How do you move BC from denominator to denominator in the last term?
Okay, so here I have Q. I'm going to take this term and move it to the other side of the equation. So that means I'm going to have Q times 1 plus UA over 2 rho CPVC. 1 plus. Now I divide by 1 plus that. So I divide by 1 plus UA over 2 rho C CPCVC. And what was left on the other side of the equation? UA times TCN minus C, T. So this was left, that's the numerator, and the denominator is this. Is that clear?
No, the next line.
The different line. Okay, so this equation, I just copied from here, dt. Here I have 1 over tau T in minus T. 1 over tau T in minus T. And now I go to the last term. The last term is Q over rho CPV. So I have the rho CPV. This just came along for the ride from here, from the blue. And now I have Q. I just copy this. Q is UA TC in minus T over 1 plus this thing. copy this over.
Yeah, I understand that. It's just, it seems like the very last part, BC, it seems like it's in the line review.
Oh, I'm sorry. I think I just wrote it wrong. BC. Oh, that's all. Okay, because obviously I wrote it wrong. Thank you. Other questions? Okay, I'm not going to be able to finish the problem this time. I'll finish it on Wednesday. But let's see where we stand. So, this is, remember, we're going to follow our, once we get through the equations, we're going to write t greater than 0 minus t less than 0, subtract. But before we do that, we know that we have to write, we look at t greater than 0 and see if it's linear or nonlinear. And if it's nonlinear, we have to linearize it. This is a perfectly linear term. There's only one t. This is only one t. This is a constant for either less or greater than 0. This is a constant for either all the time. This is a perfectly linear factor. However, this factor is multiplied by this mess. UA depends on VC. I have UA here and a UA here. And I have a VC here, and inside here, and inside here. So what does that tell me? That tells me that this term is pretty nonlinear. So what I'm going to need to do is I'm going to need to to linearize this equation. I'm going to need to linearize. I need to linearize this term. And I want you to, what's changing? What's changing? What's changing is VC and T. They're both changing. So, something I wanted to say, and I have to remember what I wanted to say. Yes. So this term has two things that are changing. One is T, and another is VC. So this term depends on, is a function of T and VC. This term has a T in it that's changing, and it's got a VC all over the place that's changing, because UA depends on VC. So this term, let's call this term term. So that term is nonlinear. So what we're going to do is we're going to use this equation, and we're going to write that this term is a function of t. We're going to, well, as a function of t and vc. We're going to write it as that term as a function of t for t less than 0 and vc for t less than 0, where this is a constant. Plus the derivative of that term with respect to t times t minus t less than 0. Plus the derivative of that term with respect to vc times vc minus vc t less than 0. Where this is going to be evaluated for t less than 0, t less than 0. So I'm not going to do that now. This way you can ponder it till next time. What are we going to do? We're going to take this nasty term with lots of VCs in it, multiplied by t. And we're going to write that term by virtue of this equation. We're going to linearize it. By linearizing it, it's going to be a function of t minus t less than 0 and vc minus vc less than 0 linearly. And we're going to write it as the term, that term, its value for t less than 0. The derivative of that term with respect to t evaluated at t less than 0, constant, times t minus t less than 0, plus the derivative of that term with respect to vc evaluated for t less than 0, a constant, times vc minus vc t less than 0. Once we do that, this nonlinear mass will be approximated by a linear 3 terms, 2 of which are linear. And notice that what the linearization does is it separates out the effects of different t's from the effects of different VCs in different terms. So different effects just add. This is an approximation. They're really multiplying times all this mess. But this allows us, in the sense of a gradient, in this case, it's a plane in a 3-dimensional region. It allows us to approximate this nonlinear term close, as long as I don't get too far from the t less than 0 conditions, by something where the effects of t and VC changing add instead of multiplying. And that's what's going on with linearization. Just as in that picture I drew with the tangent to the curve in 1 dimension, in 2 dimensions I have a 3-dimensional surface of the term as a function of temperature and VC. So it's some sort of funny, complicated surface in 3 dimensions. I'm taking the tangent plane to it. If I could draw it, which I don't have any space to draw here. So I have some sort of complicated surface. And what I do is I approximate that complicated surface by a tangent plane. By the tangent plane at that point. Where that point, this is the term, and here you have t, and here you have VC. And this point is the value at t less than 0, VC less than 0. So that's sort of a pictorial representation. Not the greatest pictorial. My art teachers would not be happy. But I want you to get the idea that I have this complicated surface, which is this term, very nonlinear, and I'm approximating it by this plane, this tangent plane, at that point, and the point is t less than 0, VC less than 0. And as long as I don't get too far from that condition, t less than 0 and VC for t less than 0, that's a pretty good approximation. The minute I get far away, it's not great, but that's what we're living with in this course. Just as this is the analog of the 1-dimensional case that we did earlier. Are there any questions? Okay, so what we'll do on Wednesday is we will do this linearization, and then we will go through the exact steps. Nonlinear equation, t greater than 0, linearized. Nonlinear equation at t less than 0, subtract, solve. I will have office hours as usual today, but I will be taking them by Zoom only today because I have to work from home in the afternoon. Normally